Good day everyone. In this video, I will going to discuss to you about functions. So this is under lesson 4.4. Now by the end of this lesson, first is you will be able to determine whether relations between two variables are functions. The next one is you will be able to use function notation and evaluate functions. Then the third one, you will be able to find the domains of functions, selected functions. And then the fourth one is you will be able to use functions to model and solve real life problems. And lastly, you will be able to evaluate difference quotients. Now, let's start with the definition of a function. So, a function from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. Now, our set A here is our domain, or this is also known as our independent variable, whereas our set B, it contains the range, or in other words, these are the dependent variables. Now, this concept is very important. It's because in our surroundings, we have lots of variables that will vary with other variables. Let's say, for example, the speed of the car varies depending on the amount of fuel that is being consumed by the engine. Amount of fuel. So, as we um, press the accelerator deeply, so the amount of fuel that is being sprayed on in the fuel injector increases. Therefore, the speed of the car, or as a result, the speed of the car also increases. So the amount of fuel is our independent variable. Okay, this is our independent variable. Now, it is called an independent variable because it does not depend on the speed of the car. Whereas our variable, our another variable, which is the speed of the car, now it's very obvious that this variable will depend on the amount of fuel that is being injected by, or that is being consumed by our engine. So therefore, the speed of the car will be our dependent variable. Okay, so therefore the values of the amount of fuel are known as the domain, whereas the values for the speed of the car will be our range. Okay, so let's have another example right here in this figure. So we have we have two squares. So on the left we have the time of the day, so this is our variable number one, and then on the right we have the temperature in degrees Celsius. So in this scenario, or in our second example, we can say that the time of the day is our independent variable, or our set A, and then the temperature will be our dependent variable, because um, the temperature that is being displayed will of course depends upon the time of the day. Now, the values that are inside this blue square are the values for our domain. Say for example, at 1 p.m. the temperature is 9 degrees Celsius, and then at 2 p.m. the temperature is 13 degrees Celsius. Now, as you can see, we have two time that have the same temperature. So this one is valid. We can still classify this as a function. Now, in order for you to um, in order for you to know whether a given um, a given example or a given set is a function, so just remember this one. First is we can only consider a given set of variables a function if the first one is that we have two or more values of our independent variable that corresponds to one value of the dependent variable. Take for example, so at 4 p.m. the temperature is 15 degrees Celsius. The same with at 3 p.m. Now this one is true in the actual scenario. So therefore, if we have two values of our domain that corresponds to one value for our range, so we can call this as a function. So this is indeed a function. However, in our or in my second condition, if you have one value of the independent variable that corresponds to two or more values of the dependent variable, so this one is not a function anymore. Now, if we are going to relate this in our second example for the time of the day versus the temperature, now for a given time, let's say at 6 p.m., so it is impossible to register two temperature readings because that would be um, that is not acceptable. Okay, so in the laws of physics or in thermodynamics, so you only have one temperature reading for a particular period of time. So therefore, if that is the case in which you have one value of your independent variable that corresponds to two or more values of your dependent variable, so therefore you cannot classify or you cannot call that set as a function. Now to summarize this, if you have many to one relation, this is a function. But if you have one to many relation, now this is not a function. Okay, so again, these are the characteristics of a function from set A to set B. Take note, our set A is our independent variable, and then our set B is our dependent variable. So the first one is that each element in A must be matched with an element in B in order for it to work. So for number 2, some elements in B may not be matched with any element in A. This one is also true. And then for number 3, two or more elements in A may be matched with the same element in B. So this one is under our first case now, in which we have a many to one relation. So this is a function. Now for number 4, an element in A, which is the domain, cannot be matched with two different elements in B. So this is under case 2, in which we have a one to many relation. So we cannot call this a function. Now let's try some examples. We're going to test whether a given set is a function or not. So for our first example, we have an input values of x. So this will be our independent variable, and then our output y, this will serve as our dependent variable. So from the first two columns, we have two values of x that are the same in value. Then it corresponds to a distinct value of y, and then there's a unique value 3 that corresponds to a unique value of y, and then so on and so forth. So this one, this is a function. It's because if we're going to input 2, I mean, sorry. um okay, so for this example again, uh for a single value, for a single value of our independent variable, that is 2, we have two corresponding outputs for our dependent variable, and these are the numbers 11 and 10. So in our first example, we have a one to many relation. So for a one to many relation, this is not a function. So therefore, our first example is not a function. It's because for the same input value, that is 2, we have two outputs, and these are 11 and 10. So therefore, this is not a function. Now let's proceed to our second example. We have here a Cartesian coordinate plane with um, 5 dots. So for our first dot, for our first point, its coordinates are -2 and 3. So -2 is our x value and 3 as our y value. We assume that our value is our dependent variable, then our x value is our independent variable. So for our second point, the coordinates are -1 and 0. Then for our third point, the coordinates are 0 and -1. And for our fourth, we have 1, 0. Then lastly, the for our final point, the coordinates are 2 and 3. So in order for us to know whether this one is a function or not, so we are going to combine all the coordinates. So we have -2, 3, then -1, 0, 0, -1, then we have 1, 0, and lastly we have 2, 3. And then we are going to um, see whether for a single value of x, now if there is two or more values of y for a single value of x, so therefore this is not a function. But if for a single value of x, we have a distinct value of y, so therefore we can call this as a function. Or for two or more values of x, we have a one value of y, still we can call this as a function. But as you can observe, for -2, the y value is 3. And for negative 1, the value is 0. For x equals 0, the value is negative 1. And for x equals 1, the um, y value is 0. And lastly, for x equals 2, y value is 3. Now, we have, I guess that's two pairs of repeating values of y. The first one is we have negative 2, 3 and 2, 3. So this is an example. Okay, this 2 is an example of a many to one relation, which is a function. And the second pair is we have this one, negative 1, 0 and 0 and 1, 0. So this is still under many to 1. So still a function, because for two values of x which are negative 1 and 1, we have only one value of y, and that is 0. So therefore, we can still call this as a function. So for this example, this is a function. So this one is not a function. So next, for our third example, we have the domain. These are negative 2, negative 1, 0, 1, 2, and the range are negative 3, 4, 5. Okay, for our first pair, so negative 2 corresponds to a range value of 3, and for negative 1, so that is for a single value of our independent variable, which is our domain. We have two or more corresponding values for our range. So therefore, at this section, we found out that we have a one to many relation. So if we have a one to many relation, it indicates that this is not a function. Okay, so for our third example, this is not a function because we found out that for an input value or for a an independent value of negative 1, we have um, two corresponding values for our dependent variable or for our range, and these are 3 and 4. Next, so let's remove first the text here. Okay, so again, for our last example, we have an input values of 0, 1, 2, 1, 0, and the corresponding output values are negative 4, negative 2, 0, 2, 4. So for our third example, we are going to determine whether we have a one to many relation or many to one relation. So we found out that we have two identical input values. These are 0 on this column, and we have 0 on the last column. So therefore, we have a one value of our independent variable that corresponds to many values of our output or our dependent variable. So for 0, we have a 1. We have a 1 to um, many relation. So if we have a 1 to many relation, so we cannot say, or we cannot call this as a function. And aside from 0, we also have another identical input values, which is or which are located on columns 2 and columns 4. So we have a uh, 1 input value of 1 corresponds to um, 2 outputs. Okay, so for a single input value of 1, we have 2 output values, and these are -2 and 2. So therefore, we now have a one-to-many relation again. So therefore, for our last example, this is not a function. Okay, so next is, how about if we are given with an equation? So how are we going to test whether this equation is a function? So we have here 4 examples. So in order for us to know whether a given equation is a function, is first you need to rewrite the equation, or you need to modify a given equation such that its form will be like this. Like on the left side, you only have y, then equal to the terms that contains the x plus the constant. So the terms containing the x variable plus the constant. Or in other words, you need to uh, express, or you need to modify the given equation and express this one into y is equal to some function of x. Okay, so this is your first step, and then the last and and then the second to the last step will be assigning some values of x, and then you are going to observe what would be the corresponding y value. So still, we are going to use the our indicators, which are the many to 1 sorry, and 1 to many. Okay, so let's try our first example. So we have x squared plus y is equals to 1. So since it is not yet expressed into y is equals to some function of x, so therefore we are going to modify this given equation. So we can transpose x squared to the right side, so you have y is equal to 1 minus x squared. So in this form, we have just um, transfer the terms that contains the x variable and the constant to the right side of the equation. So we are now ready for the last step, in which we're going to assign some values of x. So let's say for x is equal to 0. By the way, for the last step, so you have the freedom to select any of values of x as long as it is a real number. So for my example, I'm going to select, or I'm going to choose x is equals to 0. So for x is equal to 0, the next thing that you should do is you're going to substitute this one here in our modified equation. So you have y is equals to 1 minus 0 squared. So you have y is equal to 1. Now let's try another one. Let's say for x is equal to -1. So you have y is equal to 1 minus -1 squared. That is y is equal to 1 minus 1. That is y is equal to 0. So we have two ordered pairs, which are the first one for x is 0, y is 1. And then for x equals -1, y is 0. Now, if you're going to plug in for as many x values as you can, still you will arrive a distinct value of y. So therefore, um, it um, this one it satisfies our uh, basic definition of function, in which for every value of our independent variable, there corresponds to a one value of our um, dependent variable. So therefore, the values are distinct to one another. So for our first equation, this is indeed a function. So this one, indeed a function. It's because for a given value of x, there is only one distinct value of y. So this is indeed a function. Now let's try our second example. Okay, for our second example, we have negative x plus y squared is equal to 1. So we'll proceed to our first step, since the given equation does not or its um, format is not y is equals to some function of x. So first thing is that we're going to transpose the negative x to the right side. So you have y squared is equals to 1 plus x. Then we're going to um, take the square root on both sides of the equation. So we have y is equal to the square root of 1 plus x. Next is we're going to assign values for our x to see if ever we have a one to many relation, or many to one relation, or one to one relation. Okay, so I forgot to include that one. Oh. So for you to tell whether a given equation or a given set is a function, so just remember this one. First is you can only say that that is a function if you have first a one to one relation. That is, for a certain value of x, you have only one distinct value of y. And then the next one is you have many to one relation. So the given example, on the other hand, the given example is not a function if you have a one to many relation. So that's it. Now let's continue for our second example here. So you have y is equals to square root of 1 plus x. Now for x is equal to 3, so you have y is equal to the square root of 1 plus 3. So that is y is equal to the square root of 4. Take note, for square root we have two values, and these are positive and negative 2. Now if we're going to represent this in an ordered pair, so we have for x equals 3, so we have 2 as our y value, and again for x equal 3, we also have a negative 2 value for our y. Now let's try another x value. So for x is equal to, let's say, 15, so you have y is equal to the square root of 1 plus 15. So you have square root of 16. So y is equals to plus and minus 4. So for this case, we have two ordered pairs. These are 15, 4, and 15, negative 4. So by looking at the ordered pairs that are being produced in this step, we can say that for a for a single value of our independent variable x, which is 3, we have two corresponding values for our dependent variable, which is our y. So therefore, we have a one to many relation. So if this is the case, so we can say that this is not a function. Okay, just like x equals to 15. So for a certain value of our x, we have two values for our y, which are 4 and -4. So we have a one to many relation. So this is indeed not a function. Now let's proceed to the third equation. For our third equation, we have y is equals to the absolute value of 4 minus x. Luckily, our third equation is already of the form y is equals to some function of x. So therefore, we will go directly to the last step, in which we're going to assign some values of x. So let's say for x is equal to 0, so you have y is equal to the absolute value of 4 minus 0. So that is the absolute value of 4. So y is equal to 4. So we have an ordered pair of 0, 4. Now let's say for x is equal to 1, you have y is equal to 4 minus 1. So that's y is equal to absolute value of 3. So y is equal to 3. Then we have an ordered pair of 1, 3. And for x is equal to, let's say we're going to assign negative numbers, let's say minus 10. So you have y is equals to 4 minus -10. So that's the absolute value of 4 plus 10. So you have the absolute value of 14. So y is equals to 14. So we have an ordered pair, -10, 14. So if you're going to continue this one for all values of x, so you will arrive a distinct values, or you will arrive distinct values of y. So if we're going to observe the ordered pairs that are, or that were being created for this step, we can say that we have a 1 to 1 relation. That is, for a given value of x, we have a we have only one distinct value of y. So for 1 to 1 relation, we can say that this equation is a function. For our last equation, we have x is equals to 14. Now, we only have the independent variable, but again, for this equation, we can also rewrite this into 0y plus x is equals to 14. And then we're going to rearrange this one, so transpose x on the other side. So you have 0y is equals to 14 minus x. So divide both sides by 0. So you have y is equal to 14 minus x, where 0. Then again, by the rules of um, rational function, the denominator should not be equal to 0. So this is an indeterminate form. Or another interpretation for this one is that for um, a given value of x, you have infinite values of y. Now, you can also um, see this effect if you're going to graph this equation x is equals to 4. Now, the behavior of the graph of x is equals to 14 is a straight vertical line. So This is our Cartesian coordinate plane. So this is the location of x equals to 14. So we have a straight line. So if we're going to generate another pair, so it will look like this. For an input of 14, so if this is a straight line, so we have lots of output values. So we have 14 0, we have 14 1, then 14 2, all the way to the positive infinity, and also towards negative infinity. So therefore we have, for a single value of our x, which is 14, there corresponds an infinite values of y. So we have a one to many relation. So therefore the last equation is not a function. So not a function. Okay. So next we'll proceed to function notation and evaluation of functions. So a function can be written in a form. So for the input, the commonly used letter is x. Now for its corresponding output, we have this notation f of x. So f here is the name of the function, because there are some examples in which um, they use another letter aside from f. So let's say we have a given function g of x. So the name of the function this time is represented by the letter g. Now if we're going to apply this to in the equation, so you have f of x, which is our y, or our output, or our dependent variable, is equal to 1 minus x squared. So on this side, it is where we can find our input variable or our independent variable. So for this example, the independent variable is x. Okay, so just remember these two notations. You have the name of the function, then you're going to use the parenthesis and enclose your input variable or your independent variable. So for this case, it uses the x, the letter x. Okay, so next is in evaluating a function. So what you need to do is simply substitute the given value of the independent variable x to the equation in order to solve for its corresponding y value. So um, in order to understand this further, so we are going to solve our first, or we're going to solve this first example. So we have, let g of x, so this is the name of the function represented by the letter g, is equal to negative x squared plus 4x plus 1. Our goal here is to find each function value, starting with letter a. So we're going to evaluate the given function at g of 2. Okay, so that is our x here is equals to 2. So you have g of 2 is equal to negative of 2 squared plus 4 times 2 plus 1. So what I'm done here, or what I did here, is that I uh, I have just substituted the value of our x to our given function. Next is to simplify this one. So we have negative 2 squared is 4 plus 8 plus 1. So that is positive 5. So our g of 2 is indeed equal to 5. Now for letter B, we have g of t. Again, whatever expression or a numerical value that is inside in the parentheses, so this will be the input value, or this is the value of our x. So we have x is equals to t. We have g of t is equal to negative t squared plus 4 times t plus 1. So this is negative t squared plus 4t plus 1. So this is our g of t. Now let's try the last one. We have g of x plus 2. So this time, the input value is represented by the expression x plus 2. So we have g of x plus 2 is equal to negative of x plus 2 squared plus 4 times x plus 2 plus 1. So simplifying, we're going to expand the given binomial. So that's negative of x squared plus 4x plus 4. Then we're going to distribute this one. So that's plus 4x plus 8. And then plus 1. So distribute the negative sign. So you have negative x squared minus 4x minus 4 plus 4x plus 8 plus 1. So we have negative x squared. We have negative 4x and 4 and positive 4x here. So this will become 0. Then we have negative 4 plus 8, that's positive 4. So we have negative x squared plus 4 plus 1. So this is our g of x plus 2. So this is how you are going to evaluate a given function with known input or independent values. Next is we're going to evaluate a piecewise function. For the information of everyone, what you see here is a piecewise function. Now the reason why it is called a piecewise function, because for a given values of its domain, just like this one, so we have x less than 0, so that is all real numbers from negative infinity to 0 but excluding 0. So we're going to use the parenthesis. So for this particular domain, the function will hold true if x squared plus 1 exists. So you can only use this expression x squared plus 1 if the given value of x is within this boundary negative infinity towards 0. So in other words, for values of x that are greater than 0 or that are equal to 0, so you cannot use x squared plus 1 instead. So we have here a second domain, that is all values, all real numbers that are, or x is all real numbers that are greater than or equal to 0. So for this particular domain or range of values of x, you can only, or the function will only exist if you're going to use this one, x minus 1. Okay, so let's try. The first one is when x is equal to negative 1. So the first question is, on which domain is x is equal to negative 1 belongs to? So negative 1 is a negative real number. So from the given set of domains, we can say that negative 1 is under x less than 0. So therefore, we're going to use x squared plus 1 instead of x minus 1. Okay, so we have negative 1, isn't it less than 0? So this is okay. So the f of negative 1 is equal to this first expression. So again, use the first expression. So f of -1 is equals to x squared plus 1. Okay, I forgot to substitute, so I'm going to substitute it right here. So -1 squared plus 1, so it will become positive, so that's 1 plus 1 is equal to 2. So therefore, at x equals -1, the corresponding y value is equal to 2. Now let's try the second one, that is when x is equal to 0. So if the value of x equals 0, so we can say that um, this x value is under the given domain. X is greater than or equal to 0. So for x greater than or equal to 0, so we're going to use the second expression on the piecewise function. So we have f of 0 equals um, the second expression is we have x minus 1, so that is 0 minus 1, so that is -1. And then finally, when x equals to 1, so this is under the second expression. So for x greater than or equal to 0, so use the second expression. So you have f of 1 is equal to 1 minus 1, and that is equal to 0. So these are the values for our function evaluated at -1, 0, and 1. Okay, so the procedures here are most suitable for a piecewise function. So the challenge here is to select the proper expression for a given value of x. So therefore, the first step is to make sure for a given value of x, make sure to know where it belongs, on what domain it belongs to. Next is we'll proceed to the domain of a function. So the domain of a function is simply the set of all real numbers for which the given function is defined. Or in other words, these are the set of x or independent values. Okay, so we have here 4 examples. So let's try the first one. So we have a given function f whose ordered pairs are -3, 0, -1, 4, 0, 2, 2, 2, 4, and -1. So since by definition the domain is a set of all real numbers for which the given function is defined. So for our first example, the given function is defined by these ordered pairs. So what we need to do is simply make a list of the um, x values that are present. So we have for the domain, for our first ordered pair, we have -3 as the x value, second is -1, third is 0, fourth is 2, and finally we have 4. So therefore, this is the domain of this function. Now for letter B, we have the function g of x is equals to 1 over x plus 5. Now, the domain here is most concerned with the denominator. Take note, our given function is a rational function. Now for irrational function, the major restriction for this is the denominator, because the rational function expressed to p of x over q of x, such that in the denominator it will be not be equal to 0. Okay, so what makes the denominator 0? Now, by observation, when x equals -5, it will of course equal to 0. So how did you do that? First is, for a rational function, you need to equate the denominator to 0 and then solve for x. So that's x plus 5 equals 0. So the reason why we did this, because we need to know what value of x that will make the denominator 0. So that's x equal to -5. Okay, so this is the only value, this is only the real number that will make this rational function um, undefined. Okay, so the domain here, once we've analyzed this one, that is all real numbers except -5. So this is the domain for letter B, all real numbers except -5, because -5 will make the denominator 0. For letter C, the volume of a sphere, which is represented by this formula, V is equal to 4/3 pi r cubed. Now, for the case of the sphere, of course, the radius r should be a positive real number only. Now, this is also understandable. It's because r, or the radius of the sphere, should be a positive number, not a negative one, because in reality we don't have a negative radius. So this one is only valid for positive real numbers only. Now we can also, or we cannot use a 0 value for our radius. It's because for a for an r equals 0, we cannot create any space, or we cannot create any volume for a sphere. So therefore, the domain of this function, that is the volume function, are all, so the domain are all positive real numbers. Okay, so that's it. R must be a positive real number. Finally, we have h of x is equals to square root of 4 minus x squared. So for radical expression, especially if you're dealing with an even index, so for even index, what you need to do is you're going to make sure that the radicand, or the expression inside the radical symbol, should not be less than 0. Okay, less than 0, because the numbers beyond 0 towards the left are all negative real numbers, and it will make the radical expression invalid, especially for even index. So therefore, we're going to restrict the expression inside the radical symbol, which is 4 minus x squared, to be um, greater than that is greater than or equal. Okay, so greater than or equal to 0. Now 0 is allowed inside the um, radicand symbol because square root of 0 is still 0. So next, we're going to transpose this on the other side. We have negative x squared is greater than or equal to negative 4. So we're going to multiply negative on both sides of the equation. We have x squared. Now, since you multiply negative, so the direction of the inequality sign will be reversed. So less than or equal to negative. Okay, less than or equal to positive 4. I'm going to erase this one. Okay, so for this, we're going to take the square root on both sides. So you have x is less than or equal to square root of 4. Now, in this case, since we have two roots for our square root, so we're going to consider the positive root and the negative root. So for positive root, you have x less than or equal to square root of 4, that is 2. Okay, so that's for the positive root. For negative root, that is negative x is less than or equal to 2. Then we're going to multiply negative on both sides. So you have x is greater than or equal to negative 2. Now if we're going to combine these two inequalities, we can say that negative 2 is less than or equal to x, then x is less than or equal to 2. So um, the domain are real values of x from negative 2 to 2. Okay, so that's it. Next is we'll proceed to the application of function. So for this problem, this is all about the path of a baseball. So we're going to read this one. We have a baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. So the path of the baseball is given by the function f of x is equal to negative 0.0032 x squared plus x plus 3, wherein x and y are measured in feet as shown in the figure below. So with the question is, will a baseball clear a 10-foot fence located 300 feet from home plate? As you can see, this is the graph of our baseball path. So the graph of this function is represented by f of x equals to negative 0.0032 x squared plus x plus 3. Now, in order for us to know whether this baseball will clear a 10-foot fence located 300 feet from home plate, so before that, let's have some um, like additional information with regards to the motion of the baseball. Now, if the baseball is being hit, so it travels through the air following this parabolic path or projectile path. This path, luckily, is represented by the given function. So this is one importance um, of studying this concept. Okay, so the baseball path is represented by this equation. Now we're going to evaluate this function f(x) is equals to um, negative 0.0032 x squared plus x plus 3. Now in order for us to know um, whether the baseball will clear the 10 foot fence, okay, so actually what happened is that we have here a baseball bat, then it is thrown upward following the projectile path, and then let's say at 300 meters, this is the range of the projectile, So we have here a 10 foot fence. Now let's say if what is the height of the baseball bat relative to the ground at 300 meters from its starting point. So therefore, we're going to let x is equals to 3000, and not 3000 but 300 meters. Sorry, 300 meters only. X equals 300 meters. Okay, so again, the function f of x talks about the height of the baseball relative to the ground. So that's f of 300 equals negative 0.0032 times 300 square plus 300 plus 3. So we have f of 300 is equal to, now I'm going to use my calculator here, that's 300 plus 3, that's 15. Okay, that's 15, and then the unit for this one is feet. Okay, so at x equals 300 meters, we found out that the height of the baseball is 15 feet, which is way above the height of the given fence, which is 10 feet. So therefore, since 15, or the f300 is greater than the length of the, I don't know, not the length but the height, equal to the height of the fence, therefore the baseball will clear a 10-foot fence. Okay, so that's it. After we get this answer, that is 15 feet, so next is we're going to compare this to the height of the fence, and it was found out that this is way much higher compared to the fence. So therefore, the baseball will indeed clear this particular fence. So next, for our last application, we're going to evaluate difference quotient. So this one is very important, especially if you're going to pursue calculus 1. So this tool is very useful, especially on the first part of the subject on calculus. So here we have a given function f of x equals x squared minus 4x plus 7. Now our goal here is to find the function of x plus h minus the original function all over h. Now our answer here is 2x plus h minus 4, and such that h should not be equal to 0, because of course this is a rational function. So we're going to follow the rule in which the denominator should not be equal to 0. Okay, so we're going to rewrite this, that is f of x plus h. So how are we going to solve this? Using our original equation, so that would be equal to x plus h squared minus 4 times x plus h plus 7. Now we're going to expand this, that would be x squared minus 2hx, then plus h squared, then here that's negative 4x minus 4h plus 7. Okay, so next is we're going to simplify this further. We have x squared minus 2hx minus 4x minus 4h plus h squared plus 7. How about the given function like f of x, or simply just copy this one, x squared minus 4x plus 7. So the next step is we're going to substitute this to our expression. So we have f of x plus h minus f of x all over h. So now is the substitution of the expression. So that is x squared minus 2hx minus 4x minus 4h plus h squared plus 7 minus x squared minus 4, this one is plus 4x, and then minus 7 all over h. Now we have x squared minus x squared, so this one will become 0. Next, negative 4x plus 4x, this will be 0. And then we have 7 minus 7, this will become 0. So what's left is we have h squared, then minus 2hx, then minus 4h all over h. Now, by observation, we have a common factor. Now let's try it here. Let's rewrite this here. So we have h squared minus 2hx minus 4h all over h. Now we're going to factor out h. This will become h times h minus 2x minus 4 all over h. So this will be cancelled out. What's left is h minus 2x minus 4. Okay, so is my solution right? Let's try to review first. I think we have a problem with regards to the sign. Okay, I already spot the error. So the error occurs right here when we expand this binomial. So as we expand this binomial, take note that since the operation between the two variables x and h is addition, so therefore this will be addition, and also this one. So in this part we have x squared instead of minus, that's plus 2hx, so therefore this will become positive. As a result, h squared plus 2hx minus 4h over h, so divide by h both sides, so we have h plus 2x minus 4, and this is the final answer for evaluating difference quotient. And make sure to indicate the restriction in which the h, again, although this is not expressed in terms of h, but still, or although it doesn't have any it doesn't have any denominator containing h, but still we need to we are going to include the restriction for this given function. Okay, so that's it for this video. I hope you learned something. Thank you and God bless.